All right, so we'll get started again. Friday, so you guys will have your exam 3. All right, and then for the person in quarantine, you will make up your exam after you return. Okay. Just keep in mind it's going to be a separate, a different version of the exam, but so the chapters cover again will be from 7 to 10 plus the first section in chapter 11, or the same content in homework number 7 through 9. Okay. And again, you have number 10 assignment already up online. You can work on that if you have time. Classroom in disinfection today is assigned to Isaac and Nathaniel. Okay. All right. So briefly, last time we talked about the Newton's law of gravitational universal gravitation. So the magnitude of force, the gravitational force, is given as G times capital M small m times divided by R squared. So capital M and small m are the masses of the two objects, and R is the separation between the center of mass of the two objects. Okay. This G is the gravitational constant 6.674 times 10 to the minus 11. All right. Keep in mind that the gravitational force, they are actually so they are attraction forces. So that means if you have two objects, then the forces on each of object, it's having the same magnitude given by the equation, but they are in opposite direction. Okay, so attract force pointing towards each other. Okay. For the object near the surface of the Earth, then the gravitational force would be, again, can be calculated by the Gm, capital M, small m divided by R squared. That is the mg, the weight of the object. So then small g, the gravity, is given then as capital G, capital M divided by R squared. Okay, and then I'm plugging the numbers, you'll figure out it's around 9.8 meters per second square. The direction of that G is pointing towards the center of the mass of the Earth. Okay, so and then we also call that as gravitational field. Okay, for any object in the space. So then for the weight that is measured on the surface of the Earth, because Earth has the rotation, so then it's actually the apparent weight. It's not real weight. It's differ by a small amount from the actual weight. Okay, by this small amount due to the rotation of the Earth. Okay. All right. If for some reason you are inside the Earth's crust, then the G then actually then will vary throughout the Earth. Okay, so if you assuming it's going to be uniform density distribution, then there's this green curve, but for real scenario, it's more like this. Okay, because the density of the Earth is not uniform throughout the body, so more like that for the model predict. Okay. Um, Gravitational potential energy within Earth is going to be mgy, but that's assuming we are on the surface of Earth and then the y position doesn't change significantly. So then you will have that equation. But in the case if the y position changes significantly compared to the radius of the Earth, then you will use integration to calculate the change in potential energy. So then from initial to final is given then at the end by this equation. So then the gravitational potential energy should be modified slightly more accurately expressed by this equation. Okay, capital G, capital M, the mass of the Earth times the mass of the object divided by the distance between the object and the center of the Earth. Okay, so that's R there. All right. So with that modification in the potential gravitational potential energy, then the conservation of mechanical energy equation should be modified slightly as well. So you'll take kinetic energy again 1/2 mv squared, but the gravitational energy to be minus g m small m divided by r. Okay. And we can also calculate escape speed by assuming at the infinitely far away from the Earth, the velocity, kinetic energy is 0, and then also the gravitational potential energy is 0. Okay, so then at the end, escape velocity can be calculated as the square root of 2g, the mass of the planet divided by the radius of it. Okay, this also applies to other planets as well. All right. Today we are going to check satellite orbits, okay, and then the energy of satellite. So assuming you have a satellite that is orbiting on this orbital here, so then this is a circular motion, okay? So assuming it's going to be a circular motion, okay? So most of the satellites we launch into air that are having circular motion. Um, some of them may have other shapes, elliptical orbit, but that's assuming this is a circular orbit here. So then this is circular motion. You have the force on the satellite here should be the gravitational force from the Earth to the satellite. Okay, so then it's capital G M of the satellite, M of the Earth divided by R squared. That should be equal to its mass times centripetal oscillation because it's circular motion. Okay, and um, oscillation, centripetal oscillation should be v squared divided by r. V will be the speed at that orbit. Okay, so mv orbit squared divided by r. And then if you look at the very right left end of equation and then the very right of equation, you can set up the two equal to each other and then solve for this v orbit. Okay, so the r will cancel out one, the square there. Small m will cancel out, so it doesn't depend on the mass of the satellite. Velocity of this orbit will be equal to square root of capital G, capital M of the Earth divided by the orbital radius of the satellite R. Okay. All right. So that's the equation you can use to calculate the velocity at that particular orbit. Now, velocity at that orbit can be also calculated by using the circumference of the orbit, 2 pi r, divided by the period it required for the satellite to complete one cycle, right? So then, and we also have this one in the previous slide that can be calculated in that way. So you can just set this guy equals to this, all right? Then you can solve for the orbital period. So orbital period then will be calculated by setting 2 pi over r equals to square root of g m over r, okay? So then t is equal to 2 pi, okay? It's actually going to be 2 pi r divided by this square root. Okay, so then it becomes this. Okay, so given the radius of the orbit, you can calculate this also the period in there by using this equation. Okay, now these two equations, the orbital speed and the orbital period, can also apply to any planets that is circulating the sun, okay, because that's the similar scenario as the satellite is circulating around the Earth, okay. So you can do the same thing there. All right, let's take a look on the first example of the day here. So this one says two planets in a circular orbits around a star have speeds of v and 2v. What's the ratio of the orbital radius of the planets? And then what's the ratio of their periods? Okay, so you're looking for T1, you're looking for actually the first one will be the R1 over R2 or R2 over R1 either way. And then the other one will be T1 over T2 or T2 over T1, okay? You can use the equation for the orbital speed and then also the equation for the period, orbital period. So that's in the previous slide over here. So just capital M, okay? If you apply this to the sum, this should be M of the sum. Here it should be 2 pi square root of R to the Q, G, capital M, okay? All right, so let's take a look here. So V will be the V orbital, right? V1. So V1 then is square root of capital G, capital M divided by R1. V2 then will be square root of capital G, capital M over R2, okay? So you're looking for R1 over R2. So you can actually set this up over here. You can do V1 over V2, okay? That would be square root of capital G, capital M over R1 divided by square root of capital G, capital M over R2, okay? So capital G and capital M are the same, they will cancel out, all right? So then this is just square root of R2 over R1, okay? V1 over V2, that would be equal to 1/2 because V1 is V, V2 is 2V, okay? So then equals to square root of R2 over R1. So you can square both sides of the equation, then 1/4 will be R2 over R1. So then if you're looking for R1 over R2, then that would be 4, okay? All right, so that's the first part there. And then for the second part over here, You are looking for T1 over T2 now. So then you can set that up, T1 over T2. That should be equal to T1 will be 2 pi square root of R1 to the Q, right? Divided by capital G, capital M. T2 will be 2 pi square root of R2 to the Q, capital G, capital M. Okay. So then 2 pi again will cancel out. GM and GM will cancel out, right? So this is square root R1 over R2 Q, right? R1 over R2 is from here is 4. So 4 to the Q square root, okay? That will give you 8, all right? Okay, so this guy will be 8, equal to 8, okay? Now, if you are doing the other way around, if you are doing R2 over R1, then the first one will be 0.25, the second one will be 0.125, okay? So I think I got responses from both versions of the ratios, okay? All right. So if you guys are clear, we can take a look on a second example here. So this one says calculate the mass of the sun based on data for Earth's orbit and compare the value obtained with the sun's actual mass. Sun's actual mass is roughly 2 times 10 to the 30 kilograms, okay? The Earth's orbital period on average, it's about 365 days, a little bit more, because every 4 years we have a leap day added to a year. So roughly 365.26 days, okay? Use that as the period T. Its average radius is 1 astronomical unit, okay? So that's defined. The distance from the Earth to the Sun is defined as 1 astronomical unit, which is roughly 1.496 times 10 to the 11 meters. Okay, so that's R. You are given T. So you're given T and given R, so you probably can use this equation here, okay, up here, and then calculate for M. Given that, so T equals to, you are going to use T equals 2 pi square root of R to the Q capital G capital M. And then capital G is 6.674 times 10 to the minus 11. Okay. So then you're looking for capital M here. Now T is 365.26 days. Okay. We want to convert that into minutes of seconds here. So 24 hours, and then each hour there's 3,600 seconds. Okay. This is hour per day. This is second per hour. Okay, that will give you the seconds there. So you have to rearrange the terms. Okay, you'll divide both sides by 2 pi equals to square root of R over Q, R to the Q, capital G, capital M. Then you're going to square both sides of equation. So square that, okay. So then T squared divided by 2 pi square equals to R to the Q over capital G, capital M. All right. Then capital M will be equal to, you can multiply both sides by capital M, get rid of that, and then divide both sides by this. Okay, so then it will be R to the Q over capital G divided by T square here, and then further divide by that. So that goes to the top there. Okay, so this is what you have. R to the Q, R will be 1.496 times 10 to the 11 in meters to the Q, divided by 2 pi, or multiplied by 2 pi squared, divided by G, negative 11. And then T will be that number. I didn't calculate that number, but put that guy in here and then squared, okay? So if we put everything in the calculator correctly, this should be 1.9897 times 10 to the 30, okay, kilograms. And this is how the mass of the sun is being estimated, okay? And similarly, you can estimate the mass for the Earth by taking the moon's orbital, okay, right? If you can look up like how many days the moon goes one full cycle, and then what's the distance from the moon to the Earth, so you can determine it that way, okay? All right. So next, let's take a look on the energy in the circular orbit, okay? So again, you can start from here. The gravitational force equals to the centripetal force, mv squared. So you can calculate what's mv squared and then put 1/2 in front. That will be your the kinetic energy. Okay, so kinetic energy will be 1/2. So then it will be 1/2 of that. Okay, so gm capital M divided by 2 means 1/2. Okay, times r in the bottom here. So that's your kinetic energy. All right. And then for the potential energy, we say earlier in the chapter, we check it, it's going to be minus G capital M small m divided by R, okay? So the first term kinetic energy is 1/2 of it, that guy. So then the total energy will be 1/2 of the gravitational potential energy, okay? Will be capital G small m capital M divided by 2R, okay? That will be your total energy for the object orbiting around the Earth, okay? All right. So with that, let's take a look on this one here. It says the spaceship 4,500 kilogram is in a circular orbit 220 kilometers above the surface of the Earth. It needs to be moved into a higher circular orbit of 380 kilometers to link up with the space station at that altitude. How much work do the spaceship's engine have to perform to move to the higher orbit? Ignoring any change of mass due to the fuel consumption, use the mass of the Earth as 5.98 times 10 to the 24 kilogram and the average radius as 6,371 kilometer. So in this case, the force, okay, that the engine has to encounter is the gravitational force, right? So then you'll be looking at, you are basically looking at what's the total energy change, okay, from one orbital to the other orbital. That would be the how much work is done by the engine, okay? So then work is equal to the change in the total energy, okay? Will be E2 minus E1 then All right, total energy E is equal to minus G capital M small m divided by 2R. Okay. So then you are going to do it this way. Now just keep in mind for the R, it's going to be from the center of the Earth to the orbital, right? Right. So then for R1 will be, so this is the first orbit and then the second orbit somewhere higher. Okay. So R1 will be 6371 kilometers plus the original height, 220 kilometers. Okay. That's in kilometers. That means times 10 to the third. R2 will be 6371 plus 380, the second orbit. Okay. So times 10 to the 3 in meters, right? So then this is minus, we can actually put the, so this G is constant, M is not changing, this is not changing, this is not changing. So you can put everything in front, so it'll be minus capital G, capital M, small m divided by 2, right? And then 1 over R1 minus 1 over R2, okay? That would be the change in the energy if you single out the common factors in front, okay? So then you don't have to putting everything into the, oh, actually, I think it's going to be 2 in front. Yeah, because it's E2 minus E1, okay? So then minus of 6.674 times 10 to the 11 minus 11 times the mass of the Earth, 5.98 times 10 to the 24, okay? Times 4,500. So I'm not putting the units here because I know everything is in SI unit, okay? Then 1 over this guy times 10 to the third minus the other one, 1 over 6371 plus 220 times 10 to the third. Okay. Yeah, a lot of numbers there, but at the end, this is 3.23 times 10 to the 9 joules of energy required. Okay. All right. So we can move on to the next section here on Kepler's laws of planetary motions. Okay, so this is based on a lot of data like a couple hundred years ago when Kepler proposed this. Okay, so this is from experimental result. Okay, so I think we are not going into the details of theory behind, but it's basically on the observation of a lot of the stars, the movement of stars, and etc. Okay, and then planets. So basically, there are 3 laws. The first law, first Kepler's law, actually says that every planet moves along an ellipse with the sun located at the focus of the ellipse. Okay, and an ellipse is defined as the set of all points such that the sum of the distance from each points to the two foci is a constant. Okay, so you guys probably know this how to draw an ellipse. So if you put the 2 pins at the two foci there, and then you can actually have a string. You can tie the 2 ends together so that it's fixed. Okay, so you can draw just through that. Okay, if you are drawing a circle, you just need a string and then a pin. Okay, but for ellipse, you need 2. Okay, there are 2 the points that is closest approach of a planet to the sun is called the perihelion, and the farthest point is called the aphelion. Okay, so A and B there. So the perihelion on this side, and then aphelion on this side. Okay, and then this is the planet here. Now, the Earth is actually orbiting the Sun at almost like a circle. So that means that the two foci here, they are almost identical at the center. Okay, so that's basically the first law there. And then a circle is a special ellipse, okay, with the two foci points at the same point. The second law, Kepler's second law, says that a planet sweeps out equal area in equal times. That is, the area divided by time, called the areal's velocity, is constant. Okay, so here, say from point A to point B, and the time it spans for the planet spent over here is the same as from C to D, and then the same from E to F. So if that's the case, then the area here, A1, A2, and A3, they are the same. Okay, they should be equal to each other. A1 equal to A2 equal to A3. Okay. And in that sense, you can see that. So then when the planet is close to the sun, then it has higher speed, right? Because for the distance travel here is higher at the same time. So then at the farthest point, then the speed will be the smallest, okay? Will move slowest, okay? All right, so let's take a look the Halley's Comet here. It says the perihelion of Halley's Comet is 0.586 AU. AU stands for astronomical unit, which is the distance from the Earth to the Sun. And the aphelion is 17.8 AU. Given that its speed at perihelion is 55 kilometers per second, what's the speed at the aphelion? All right, I think I'll give you guys a few minutes to solve for this one. We can take a look at the solution together in a few minutes, okay? All right. So let's see here. So according to the Kepler's second law, if the time span is the same, then it will sweep through the same area. So that means, so let's say from here to here, it takes delta t, and the same here would be also delta t, okay? From here to there will be delta t, okay? So then these two areas should be the same. So A1 will be equal to A2, okay? Now my figure doesn't quite show that, but that's assuming they are the same. All right. Now we can actually, so this is kind of like the arc length over here, right? So then for this area, I don't think we have a specific formula for that, but we can assume that delta t is going to be very small, okay? Approaching to 0. Then if that's very small, then if you zoom into this side, then it's probably look like something like a triangle, right? With this end being V1 times delta t, right? And then the height of that would be the R1, okay? So then A1 will be equal to 1/2 the base times the height, right? Equals to 1/2 V2 delta t, the base on the end, times R2, okay? In that sense. So in that sense, you can see the time doesn't matter because it will cancel out, okay? 1/2 doesn't matter as well. That will cancel out, okay? So then V1 R1 should be equal to V2 R2, okay? So this is what you will arrive at. Now you're looking for V2, so then V2 will be equal to V1 R1 divided by R2, okay? So take 55 kilometers per second times the 0.586 AU. You can keep that unit because it's going to cancel out the unit down here, right? So you don't have to convert that into meters actually. This is going to be roughly 1.8 kilometers per second, okay? So in that sense, pretty much if you are at the aphelion or perihelion, then it's V1 R1 equal to V2 R2, okay? Because at those 2 points, the velocity and R are perpendicular to each other, okay? All right. So in general, other places other than the aphelion or perihelion, then R and V is going to have an angle of theta, right? It's not going to be 90 degrees, but it's going to have an angle of theta. So then in that sense, so then the area here swiped over here, okay, you'll be looking at this area, okay? And then, so what you are going to do, you are going to have, so this, for the area of here, you are going to have this one side times the height, right? So you're going to have like R times V delta T. So this is V delta T if the time span was small delta T. So then you can see this is VT sine of theta that gives you the height, okay? It's not exactly VT delta T, but V delta T sine theta over there, okay? So then in that sense, the area should be written as, let me use my paper here. So then the area is going to be written as R times V times delta T times sine theta, okay? So that's equal to constant, right? Because it says at the same time, delta T will sweep out the same area. So then that means if delta T is constant, then area will be constant. Now you can also multiply this by M, right? So then M or this is A1, let's say at one particular point. So then R1 V1 sine theta 1, okay, delta t. Now, a second time, if you are at a different location, say anywhere, maybe somewhere here, right? It will still be the same time. So then A2 here will be R2 V2 delta t sine theta 2. The theta will be then between R2 and V, okay? So these two should equal to each other. Now you can multiply this guy by mass of the planet, okay? And then this guy by the mass of the planet. So then MA1 should be equal to MA2 as well, right? If you just multiply them by the same mass of the planet, so that will be equal to each other. So then MA1 will be this, R1 V1 delta T sine theta 1, okay? It's going to be equal to MR2 V2 delta T sine of theta 2, okay? So it really turns out that delta T and delta T will just cancel out, okay? And then you can keep the rest over here. So then this would be, so R1 here. So you can put R1 in front, MV1 sine theta 1, okay? And then equals to R2 MV2 sine theta 2. So this is the momentum, right? P1. So it's R1 P1 sine theta 1 equals to R2. This is P2 sine theta 2, okay? So if you remember, when we are talking about angular momentum, so this is actually angular momentum for the point mass, right? R cross P, which means RP sine theta, right? For the angular momentum. So this is actually conservation of angular momentum, all right? So Kepler's second law, it's actually just another expression for the conservation of angular momentum for the point mass, where the point mass is in the planet, okay? All right. So it's basically conservation of angular momentum there. Lastly, the third law, Kepler's third law, it says that the square of the period is proportional to the cube of the semi-major axis of the orbit, okay? So then this is the equation. So t squared is equal to 4 pi squared divided by capital G, capital M, and then times a to the q, okay? So a is the semi-major axis of the orbit, okay? Which I think it didn't, let me see. It didn't define specifically what's the semi-major axis. So a, so that's let me use this guy. Let me use this figure, okay? So the semi-major is equal to, so if this is a, if a is this distance, if b is this distance over here, okay? Or I should say just use R1 and R2, okay? So then A is equal to 1/2 of R1 plus R2, okay? So which will be this guy, half of this, okay? From here to here, okay? So in that case, if this is a circular orbit, then it will be just the radius of the orbit, right? Okay, so that's the semi-major axis of the orbit. A equals to 1/2 of R1 plus R2, okay? All right. So then again, if it's this is a case of circular orbit, so then R is the A, okay? So then T will be just taking square root of this thing, which is this guy, which happens to be the period for the circular orbit we learned at the beginning of the class, okay? It's the same equation if you go let's see, if you go just up here, yeah, it's the same this, okay? If this is a circular orbit, then it's this guy here. All right. Okay, so let's take a look on this one here. It says the perihelion of the comet Lagerkvist is 2.61 AU, and it has the period of 7.36 years, show that the aphelion for this comet is 4.95. So you want to use the equation in the previous slide that t squared is equal to, let me see what's that. It's equal to 4 pi squared divided by capital G capital M times a to the q, where a is equal to 1/2 of R1 plus R2, aphelion plus the perihelion. Okay, so that's that guy there. So on this one, you are looking for the perihelion, and then you want to show that it's equal to 4.95 AU. Let's take a look here together, okay? So then for this comet, we'll call it the period for it will be like t of this comet. I'm going to say t of c square is equal to 4 pi square divided by capital G. Capital M will be the sum, the mass of the sum, okay? And then a to the q, that's going to be, or I can just use a to the q. So I can solve for a to the q first and then solve for R2, okay? So R1 is the aphelion, which is the or the perihelion 2.61 AU, and then R2 is what I'm looking for. So if I can solve for A, I can solve for R2, okay, from here. So you can look up the mass of the sun, okay? And then you can calculate this guy first in terms of AU and then calculate that. But I'm going to just use a reference here using the period for the Earth, okay? As an example here. So TE square equals to 4 pi capital G capital M times R E to the Q, right? Or you can say AE to the Q, that's the same thing. So if I compare the two, I can set up the equation. So this is one equation, this is two equation, okay? I can do equation 1 divided by equation 2. That means, so equation 1 divided by equation 2. That means I'm doing the left-hand side of equation, so TC square over TE square. That should be equal to the right-hand side of 1 divided by right-hand side of the 2. Okay, so 4 pi square capital G capital M, A to the Q divided by 4 pi square capital G capital M, RE to the Q. Okay, so this and this will cancel out because they are the same, right? Now it tells me the period for this comet is going to be 7.36 years. Okay, so 7.36 years. I'm going to just use year as the unit. Square divided by the period for the Earth, which we all know it's going to be 1 year, right? So 1 year at the bottom here, and then a to the q divided by re to the q. So the Earth's distance to the sun will be 1 astronomical unit, right? 1 AU, right? So then if I solve for this, this will give me the A in the unit of 1 AU, right? So it's basically, you are going to do cubic root of this side, okay, and then cubic root of this side, okay. So then A is equal to 3.784 AU, okay. So once I have this guy, I can go back to that equation to solve for R2, okay. So I'm going to set A equals to 1/2 of 2.61 AU plus R2, okay. So multiply both sides by 2 to get rid of that, and then 2 times 3.784 AU minus 2.61 AU will be the R2. So in that case, R2 is exactly 4.95 AU, okay. The astronomical unit there. Okay. All right. The last section in this chapter talks about tides. So yeah, we know tides happens, right? That's because so mainly because the moon's gravity on the water in the ocean, and then compared to its gravity on the Earth itself. Okay, so when the moon is over here, it because water is liquid, right? It can move, so the shape it can move. So then this can be having slightly more gravity because the water to distance to the moon is slightly less than the distance from the Earth to the moon. Okay, so then water is being pulled over there. On the other hand, here, now the moon is pull the Earth more than the water, so then you also get high tide over there. Okay, there's also effect from the sun as well, slightly. Okay, so that's affecting the tides there. Okay, I think that's it for this chapter. Okay, so we'll finish this chapter and then finish the lecture for today as well. Okay, so and then on Friday we'll have exam 3 here. Okay.